we knew that dy dx, that's one way to write a derivative, is the same thing as f prime of x. So now we know that the differential of y is the derivative of the function times a small change in x. I know it doesn't really make any sense right now, but just wait. This symbol is called an integral. We are going to integrate, in other words, find the antiderivative of both sides of this equation. And this is the way you will see most of your questions written. We have y equals the integral of some function that is actually the derivative of some function y. What we have to do for all of this chapter is take this this whatever is this is called the integrand, the thing that you're integrating, and we have to figure out what was the function before the derivative was taken. All right, so let's see if I can squeeze all of that up here. All right. So let's look at something that we've done before. If we know that y is, let's say, 3x squared plus 2x minus 5, and we took the derivative of this, what did we do? Well, first we multiplied the power. We multiply whatever the power of x is, multiply that down, and then we subtracted 1 from the power. Now we don't write x to the 1, but you can see what happens, right? The next term, 2x to the 1, we're going to take the 1 power here and multiply the 2 by that, which gives us 2. And now what's the power on x? Up here the power was 1. When you subtract 1 from that, you get x to the 0. Well, what's x to the 0? X to the 0 is just 1. So he's not there anymore. And now what about the derivative of the constant? This guy right here. Remember, derivatives are rates of change. And if negative 5 is always negative 5 and it never changes, then what's its rate of change? 0. But another way to look at it is that if we have a constant, we have the constant times x to the 0. Now, if we took the derivative of this, a power rule derivative, we would take that 0 and multiply the 5, right? So we would get 0x to something here. So when you took the derivative of a constant, you remember that that guy went completely away. And that's important to remember when we're going backwards. So this derivative has a 0 at the plus 0 at the end of it. Now what if we go backwards and we say that y, sorry, hold the phone, and we say that y is the antiderivative of this function, which is now the derivative of something, and we're going to go backwards. Now, what did you do? I'm sorry, I'm just learning here. What did you do when you went from here to here? You multiplied by the power, and then you subtracted 1 from the power. What's the opposite of that? Go backwards. If you go backwards, do you divide and then add, or do you go in the opposite order as well? So now what we have to do is first add 1 to the power, and then the opposite of multiplying will be divide by the new power. When we do this, we'll see that we get what we started with back again. So y equals, we have 6x to the 1, but we're going to add 1 to the power and divide by the new power. Then we have plus 2. X was to the 0. We add 1 to that, and we divide by that. So you see what we have is 3x squared plus 2x, but wait a second. The original function had a minus 5. Do you remember that? Well, anytime you take an antiderivative using a power rule, and I'll write down the power rule in just a minute, anytime you do this, you have to wonder if there might not have been a constant right there. But when the derivative was taken, it was plus 0. Remember? So if we go backwards with that plus 0, when we take the antiderivative or the integral, then we have to allow for that possibility that there was a constant, okay? So this guy is called a constant of integration. So anytime you do an integral and you're not doing it on a definite interval of x values, we'll talk about definite integrals later on, but anytime that you're just finding an antiderivative, you have to stick that possibly constant term in there. So we just say plus c at the end of our integrals. All right? Whoops, this isn't working here. I'm trying. That's good enough for me. Good enough for you? Let's move a little faster here. Okay, try this one. What is the integral of x cubed minus 4x squared plus 3x minus 8? That dx is the differential of x, and it has to be there. It's an operator that works in concert with the integral to give you an antiderivative problem. So don't forget the dx. He's very important, and he's going to get even more important later on. So let's see what we're going to do. I'm going to copy my x, increase the power, divide by the new power. I'm going to copy my minus 4, my x, I'm going to add 1 and divide. Copy plus 3, copy the x, add 1 to the power, divide by the power, copy the minus 8, that was x to the 0. We're going to end up with x. Let's think about this. What's the derivative of x squared, of 8x? The derivative of 8x is just 8. So you see how that works. And we always allow for the plus constant there. And then you make it pretty. I'm not going to make you find common denominators or anything. I'm running out of room here on my board, so I'm going to be a little bit messy down here. Nothing cancels? Well, I'm wasting my time then. Never mind. None of those fractions reduce to lowest terms. So you just always make sure that your fractions are reduced. Are we good? So let's talk about some rules. I'm going to give you more than just one rule here. First, power rule integral. If we have the integral of some number, some variable to some number power, we're going to add 1 to the power and divide by the new power and allow for a constant of integration. Now, what if we were integrating just some constant? We'll call him k. If all you have is a constant, remember that that is, there's an x to the 0 right there. X to the 0 equals 1. So you're integrating x to the 0 power. When we do this integral, the k is there. We copy the invisible x. We add 1 to the invisible power, and we divide by 1 plus c. Now, ask yourself, what's the derivative of k times x? It's just k. So we know we're right. You can always take the derivative of your answer and check to make sure that you get the question back. Okay, a couple other rules that are in 4.1 that I wish were put a little bit later, but they are in this section, so we are going to do these. Remember, the derivative of e to the power is e to the power times the derivative of the power, right? So when you're going backwards, you still have e to the number x, but we need that number in the bottom. Think about what this means. I'm going to put a little thought bubble over here. Let's do the thought bubble in red. If I have y equals e to the 3x, then the derivative of y is copy e to the 3x, but then I have to multiply by the derivative of the power. So if I integrate 3e to the 3x, which is my derivative here, then I'm going to keep the 3. He's going along for the ride. I copy the e to the 3x, and I divide by the 3. You see how the 3's will cancel, and we get the e to the 3x that we started with way up here at the top. You see that? So that's why you have to divide by the n. When we get to integration by substitution, which is in 4.5, we'll understand this a lot better. All right, let's try the homework at this point. For 4.1, you can stop this video and you can try the homework in 4.1. 4.1, all of the homework is 1 through 55 odd.
Keep a lookout for the next video. In the next video, I'm just going to work a bunch of problems from 4.1 just to give you an idea of how to do it. So watch for that.